So you've learned about vectors and the basics of how to use them and how to represent lines with them. Now in this video, we're going to look at the application of vectors. In this example, we've got a yacht sailing, and because it's on the sea, then it's not really moving up and down. It's on the same level sea. So we're looking at the yacht from the top now and looking at vectors that represent its displacement going east and north. So it's a 2D situation where the movement is only on a flat surface.
So let's just look at this vector just for one moment. The first one says vector 1, 0 represents a displacement of 1 kilometer due east. So let's think about why that's east for a moment. We know that the first number in our vector represents the x, and so x in this case would be east and west, and because it's positive 1, that's moving towards the right. So here, the number 1 represents 1 kilometer east. And same thing underneath. The y component there below represents you're going 1 kilometer north because again it's positive, which means you're going up. Okay, so that's why. If it was negative, that means you'd be going south.
So at 12 noon, we start with the yacht at point A 220. Now this is a position on a grid where this represents x and y. If I were to write this as a vector, then I would write it as a column vector, and this would be its position vector from O, right? And O here, I think, being just a certain point of origin. At this stage, they're not explaining where it is, but there's always a reference point. This direction of travel is as we know, direction. When we look at the line, right, there are two points or two parts that we are interested in when we're looking at the line in vector form. The position vector, which is now this position vector from O, and this would now be its direction vector.
So I guess we've got everything we need now to describe the movement using a line. So we're going to use a vector xy, let's say, to describe that. And we'll start with the position vector, which is 220, plus, and then we'll add our scalar, lambda, and then we'll put the direction vector for -3.
So this direction vector now is explaining its direction, but if you look at that direction vector, it has its own magnitude, right? And since we're talking about movement of a yacht, which is sailing, this will probably represent the time, right? So whatever time there is, it moves 4, -3, depending on the time. But let's see what that magnitude is so we know exactly what direction it's moving. So let's take the magnitude of 4, -3. Now it says here that it's traveling at a constant speed of 5 kilometers per hour. So let's check if this actually gives us a magnitude of 5 kilometers per hour. So using our magnitude formula, or Pythagoras, we have square root of 16 plus 9, which gives us 25, or 5. So the magnitude of this is 5, so therefore its speed is 5 kilometers per hour.
So the direction vector and the speed are connected.
So there's a special name for that vector, and it's called the velocity vector.
So have a look at what that velocity vector is telling us. It tells us which way we're moving. So we're moving along the diagonal, okay? And then it also gives us an idea about the speed that we're going if we look at the magnitude. Now keep in mind, this is not a question. We're not asking you to solve for something here. We're just trying to describe the movement of the yacht.
So the magnitude here is the speed.
This is something you may have to do. Given a problem, you may have to write down the equation of the line in vector form and maybe also figure out what the speed is without being asked to do it. So always take out the information from the text and try and rewrite it in a mathematical way.
So let's look at an example now where we've actually got to use a vector to describe its movement and direction and magnitude. The tractor is moving across a field at 10 kilometers per hour on a bearing of 150 degrees. Now we have here now the north. So if it's 150 degrees, that would be, this is 90, so 150 would be over here. That would be 150 degrees. we want to find a vector or its velocity as a column vector. So we're looking for a column vector which should show us the direction and magnitude. So we know that 10 kilometers per hour is its magnitude, so the length of this must be 10 km per h. Now, how do we figure out what its direction will be? Now we know that the direction vector is always xy, where x represents the horizontal movement. So I probably need to draw a right triangle here to describe the x there, and a right triangle there, and a y to describe the movement on the vertical.
And we should have a relationship that x squared plus y squared is equal to 10 squared.
Which is the magnitude of the vector.
So how can we work out x? Hopefully this is nice and easy for us. So we go back to SOHCAHTOA, just have a look at what information you have. So the angle of 150, we can break that up quite easily. 90, of course, is the first quadrant, and left over you have 60 degrees. Okay, we know that it's 10 kilometers per hour is the speed and distance along the hypotenuse, and then we can just use cosine to find x. All right, so remember the rule, cosine is adjacent over hypotenuse, and solve for x.
By now you should know your special values for cosine 60.
Which I believe is a half.
It's a half.
So therefore our x here is 5. So the movement on the horizontal is 5 this way, or at least the length of this is 5. Now let's find the y.
So we could do the same thing with sine 60, or we could solve an equation with 10 equals square root 5 squared plus y squared. So that's a choice. So sine 60.
I like this better, miss, because I remember what sine 60 is.
And what would that be then?
Square root of 3 over 2.
Try and keep your values exact if you can, and refrain from using the calculator. Sometimes you won't have a choice if it's a paper one, but it's good practice.
Simplified, 10 divided by 2, so then we have 5 root 3. So y here is 5 root 3. Now let's describe the vector, or the velocity vector. Now if we know that this triangle now follows Pythagoras, so we're sure that the magnitude is 10. So all we have to look at now are the x and y's. Since x is 5 and it's going to the right, it should be a positive 5. And y is going down,
Which is south.
so then we go negative 5 root 3. Now, of course, you can also represent that vector by going this way first and that way, right? But since the tractor is moving this direction, we can't go the other direction. So I can't go from here going there. We need to follow the direction of the tractor. So that would give me the same thing, 5 this way and 5 root 3 this way. And since it's going down, that's negative, and since it's going to the right, that's positive.
So let's just check the question again. So we asked you to find its velocity as a column vector. So just check what you've got there. You've got the direction. So we now have a vector showing the direction that we've traveled in. And we know that, and we can check that. It does equate to 10 kilometers per hour. If we work out the magnitude of that vector, it will be 10 kilometers per hour. So effectively, it's equivalent to 5 kilometers in an hour going east, and going south 5 root 3 kilometers in an hour.
Let's try another one. This one asks us to find the velocity vector of a speedboat going parallel to this. So here's our direction vector, but the speed is 65 kilometers per hour. Now if I look at that direction vector, again, it has its own magnitude. So let's check the magnitude of this vector. Negative 5, 12, I want the magnitude, so that gives me square root of. Ms. Carter, do you know the squares of these numbers?
25 and 144. That would be 169, which gives us 13.
So that means at the moment our magnitude is 13 kilometers per hour. So this actually is not fast enough. We want to have a speed of 65 kilometers per hour. So the magnitude is not correct, what we're looking for.
We're going to have to use a scalar to multiply our vector, keeping it parallel, but increasing its magnitude in order to have 65 kilometers an hour altogether.
So if this is 13 kilometers per hour, let's scale it down to 1 unit. So if it's 13 kilometers per hour, let's scale it down to 1 unit by multiplying it by a 1 over 13.
So now we've got a magnitude of 1.
This is now the unit vector, magnitude of 1, right? And what we want is one with a speed of 65. So as you know, to make that 65. If that's 1, then I'll just multiply everything by 65. So now our velocity vector should look like this.
And we're lucky in this case because 65 divided by 13 just equals 5. And we can also multiply that into our vector.
Now, if your vector looks not so nice when it's a fraction in a fraction, it might be wiser to leave the scalar in front. But in this case, it comes out really clean. So this is now our velocity vector.
And so again, just to check, we're aiming to see that the magnitude of that vector is 65. We can check that. So 25 squared.
60 squared. We're leaving Ms. Kwanka to do all the work here. She's doing a beautiful job.
And I know this is going to be 65.
There you go.
So we've found a vector that's going in the right direction. It's parallel to negative 512 like we wanted, but now I've just scaled it up to the right size, so the magnitude is 65 kilometers per hour.
Right, let's look now at an actual problem where we've got, in this case, you can stop the video to read the question first. But it's a pleasure boat, so we've got a pleasure boat and we've also got a cargo ship. So we've got 2 boats here, and this pleasure boat leaves the harbor. So our harbor is our 0, 0, our origin, and this is its position after time t hours. The cargo ship also travels with the same number of hours. So we're using the same scalar here, but the position of the cargo ship is given by this at t hours. So it doesn't start from 0, 0 unlike this one does. So it starts from 12, 12, and we're going to represent that now in a grid. So let's look at the first one. This is our harbor ship. Right? It starts at 0, 0, and after 1 hour, it's 10, 7. So I go 10 on the x and 7 on the y, I believe that's here. Right? And if I draw a line to represent that, so this movement is after 1 hour for the harbor ship. Yeah? Find the speed of the boat. Oh, that should be easy because we have a direction vector. Right?
Remember that the direction vector is linked to your speed because we can also call it the velocity vector.
So the length of this is the speed because that in 1 hour would give me the speed per hour. Okay, so let's find the magnitude of your velocity vector. So let's keep in mind again, like Ms. Carter said, this is the velocity vector.
So, as usual, magnitude of our vector, 10, 7, we're just going to take the square root of 10 squared and 7 squared. So altogether makes 100 plus 49, so the square root of 149 kilometers per hour.
That's our speed of the pleasure boat. Did I call it a harbor boat? Yeah, I think I did. So now let's look at the cargo ship, and here we have this. Find the distance of the cargo ship from the harbor. Okay, so let me correct this. This was the pleasure boat. So now we're looking at the cargo ship and its movement. This one starts at 12, 12. I'll use purple for this one.
Why don't we mark that position on our grid, and then we know where that boat is starting from. And then we can actually indicate in which direction that boat is going. It's going 4 to the right and 1 up. And that's every single hour.
So as you can see by looking at it, it's much slower, right? You can see in 1 hour, it's definitely not moving as far as the pleasure boat.
And I extended that there just to see what its direction would be. So after 1 hour is just that. So there's going to be another hour before it reaches here, and so on. So let's get back to the question. Find the distance of the cargo ship from the harbor. Okay, so our cargo ship starts here. Where is its distance from the harbor? And I think we need a position vector.
We do. Every time you go from your origin, you are actually describing a position vector.
So this is our position vector for the cargo ship.
Yeah.
Cargo. And that position is at 1212. So from 0, 0 to 1212, there's our position vector. We want our distance from the harbor. So then we just find the magnitude of that position vector.
Remember, the distance is always positive.
Too fast? No.
Wow, impressive.
Now, if the boat, this is when it starts its journey, it starts there. Okay, so that's its distance. If the boat and ship continued on the same course, after what period of time would they collide? Okay.
So if you think about it, this should be an intersection. So we have two lines and we're hoping to see where they would intersect each other. So we can do this with equations and we can do it visually as well to check.
What would you like to do first, Miss?
I think an equation would be good. So let's have a look at our first pleasure boat. Look back at our vector at the top here. We want to see when this, so it's t, and then a vector 10, 7. We want to see when this equals the second vector. So we need the entire coordinates, not just the direction. You need the 12, 12, the point, and then the direction it's moving with that scalar t.
Yeah, so if this vector represents its position, and this vector represents the position of the cargo ship, then we want them to be in the same position. That's why we equate them.
Genau, at a particular time t.
So we need to check it's the same time t for both the x-coordinate and for the y-coordinate. So we can write two equations out. First here, you can just combine them into one vector is also what you can do. So for the x component, you have 10t equals 12 plus 4t. So we can solve that, and t is 2. So 2 hours is what we have for the x component.
We're going to have to check in the second equation.
So you can solve the second equation, or you can substitute in 2 and check. It doesn't matter which way you want to do it. And again, we have t is 2, so 2 hours. So in both cases, it makes sense that when t is 2, that yes, they do collide. There's an intersection.
I'm curious to see if we would see that on our graph. So if we extend that pink line, we should be able to show that the pleasure boat after 2 hours is exactly at that point, and it happens to be exactly the point where our cargo ship would be after 2 hours as well.
So after 2 hours, we would have gone 10 plus another 10, so that's 22. 12 plus 7 and another 7, that would be 26. Is that right?
No, it would be 14.
14 plus 12?
Yeah.
Yeah? And this one was at 10, 7. We add, is that right? Does it look the same? Am I doing it wrong?
That one would be 14, right?
Oh, 14.
There you go.
After 2 hours, yes, sorry. So it's plus 4. Sorry, I was adding the wrong vector.
So
I should
let's
be
just
adding
check.
4, 1.
So which equation? We're looking at the cargo ship, just to be clear. So we need the equation for the cargo ship. So let's think about where it starts from, 12, 12. And then it's moving for 2 hours. So you do 4, it's going to go east, and 4 again. And then in the y-coordinate, it's going to go up by 1 and then 1 again with the equation from the cargo ship.
So that's 20 and
14.
14. Thank you, Miss.
There you go.
And this one moves by 10, 7. Okay, so if I add another 10 to that, it would give me 20, another 7 to that, 14. So then they are colliding at that point, and it takes 2 hours to happen. Okay, that's it. You're off.